Let's look at a few more examples of solutions to differential equations. So for this first example, let's use this formula for x. X is capital A over t, to find solutions to this differential equation. T times x prime plus x equals 0. Sort of implicit in this setup is that t is the independent variable and x is the function, and this derivative here, x prime, is really dx dt. Okay, so when I say use the formula to find solutions, I'm being a little vague. Maybe what we should do is just plug this in to see if this works as a solution. So if x is a over t, we're going to need to differentiate this. So to do that, let's rewrite this t in the denominator as t to the minus first. So dx dt is minus a times t to the minus second, so that's minus a over t squared. Now we can plug these into the differential equation to see if it works as a solution. So t times, this is x prime, and that's minus a over t squared, plus x, and x is a over t. And we need to check, is this equal to 0? Okay, well, let's see. We can simplify here. This t cancels one of those. And so we have minus a over t plus a over t. Is that equal to 0? Yes. Yeah, that's equal to 0. But there's a problem here. So it seems like, shouldn't we, at this point, shouldn't we be able to say that a over t is a solution? It seems like it, but not quite. There's a caveat that I slipped in before about something we're going to require for solutions to our differential equations. What we're going to require for solutions is that they must be continuous. So we need any solution to be continuous. And this function, a over t, this is discontinuous, this is not continuous at t equals 0. Right? If you sketch a graph of this function, it looks something like this. At least if a is positive, it looks like this. If a is negative, it looks like this, but flipped vertically. This graph clearly is discontinuous at t equals 0. There's a big jump right here, right? As you approach t from the left, it goes down to negative infinity. As you approach t equals 0 from the right, it goes up to plus infinity. There's this discontinuity. So we actually can't use this entire function as a solution to the differential equation. The best we can do is keeping only one continuous piece of this, this function. So we have two flavors of functions for this differential equations. So our solutions come in two types. So since we need a continuous piece of this solution, we could choose the part on the right or the continuous part on the left. And those are the two types that I'm referring to. So the first type of solution, or the first collection of solutions, is x of t is capital A over t, but t has to be positive. And the second collection of solutions is x of t equals a over t, but t is negative. So if you graph these two, you can see that both collections, each function in each collection is continuous. Right? You have to throw away half of this graph of a over t to get a continuous solution. The reason why we really insist that solutions should be continuous is the idea is if you're at any particular spot somehow the differential equation tells you where to go next as you move to the right or the left. So if you start on some place on the left-hand piece of this graph, the differential equation forces you to trace out all of this blue graph. But when you have a discontinuity, that sort of breaks this guiding that the differential equation does. Essentially, since the differential equation tells you just where to go next door from where you already are, it can't jump this big gap at the discontinuity. Similarly, if you started at somewhere on the right-hand side of this graph, the differential equation would show you how to continuously trace out the red piece, but it couldn't help you jump across this gap because of the discontinuity. So that's why we're going to insist that our solutions be continuous, and that breaks this single graph up into two types of solutions for this differential equation. All right, so there's one complication that can happen for differential equations. Right, here's another example of a different kind of differential equation. So let's check that this collection of solutions is a solution to this differential equation. Now you'll see in this collection of supposed solutions, there are two parameters, so c sub 1 and c sub 2. Those are constants that could be anything. And so when I say that this two-parameter family is a solution to this differential equation, what I mean is, if you pick any number for C1 and any number for C2, that function of x is a solution. So let's see if it's true. We just need to take this function and plug it into this equation and see if it makes the equation true. Well, to plug this function of x into our differential equation, we need to calculate two derivatives because this is a second order equation. It has the first derivative of y and the second derivative of y. So let's calculate some derivatives of y. So y prime is c1 times, then the chain rule gives us a 5, e to the 5x, plus, and then for the second term we get c2, and then the chain rule gives us a minus 4 times e to the minus 4x. Okay, now we can do the whole thing again. Y double prime is c1 times, now another factor of 5 comes out of the chain rule, so we get 25 e to the 5x plus, and then another factor of minus 4, so c sub 2 times 16 e to the minus 4x. All right, now we can take all of this and put it into the differential equation and see if it all adds up to 0. So y double prime, which is c1 times 25 e to the 5x plus c2 times 16 e to the negative 4x. Okay, so now minus y prime, so minus y prime is c1 times 5 e to the 5x minus c2 times 4 times e to the minus 4x. So I've taken this minus sign and just made that addition and subtraction instead, plus 20y minus 20y, sorry. So 20 times y is c1 e to the 5x plus c2 e to the minus 4x. Okay, so this is all supposed to add up to 0. Let's see what we get when we simplify this. So let's see. For all of my e to the 5x terms, they all also have c1. So let's factor c1 e to the 5x out of those terms. We have a 25, and then a minus 5. Don't forget to distribute that minus sign. And we have a minus 20. So that's the e to the 5x terms. Now let's add up the e to the minus 4x terms. They all have a c2. So let's factor out c2 e to the minus 4x. And we have a plus 16, a plus 4, right? It's plus 4 because this minus sign, when you distribute it, makes that a plus. and then minus 20 from distributing this minus 20 there. And when you add all of those up, yes, you do indeed get 0. So this 2-parameter family of solutions really is a solution to this differential equation. Whether it's all solutions, we don't know, but at the very least, it's a lot of solutions. Okay, final example for solutions to a differential equation. Let's look at this differential equation. dy dx equals x over y, and let's show that it has this for solutions. Now this is an equation, x squared minus y squared equals k. And you might protest because I did say a little bit ago that solutions to differential equations should be a function, but this sort of equation, it doesn't exactly give you a function, but it almost does. You might recognize this kind of equation. It's actually a hyperbola like this. And it's not quite a function because it doesn't pass the vertical line test, but if you look at any point, almost any point on this curve nearby, if you look just at the graph nearby, it is a function, as long as you stay nearby, right? You have to go very far away from this point before the vertical line test fails, right? And that's true for almost every point on this graph. Near almost every point, the graph passes the vertical line test. So an equation like this it will count as a solution to the differential equation. Now the key thing here is that near all the points, these are all continuous. Okay, so let's verify that this is a solution to this differential equation for any value of k. How could we do this? I mean, we need a derivative of y, but what we have isn't y as a function of x. What we have is an equation that involves x and y. So how can you find the derivative of y when you just have an equation? Well, that's a job for implicit differentiation. So let's find dy dx by using implicit differentiation. So remember, the idea with implicit differentiation is when you have an equation like this, to find dy dx, just differentiate both sides with respect to x. On the right-hand side, this is pretty straightforward because k isn't a function of x, right? K is a constant, so when you take its derivative with respect to x, you get 0. On the left-hand side, just differentiate, but remember that x is an independent variable that we're differentiating with respect to, and y is secretly a function of x. We're treating y as if it's a function of x. Okay, so when we do that, derivative of x squared is 2x minus, and now we need to take the derivative of y squared. But again, remember, we're differentiating with respect to x. So y is a function of x, so it's as if we have an inside and an outside here. So we need to use the chain rule, right? The outside function is the squaring, and to take the derivative of a squaring, you do 2 times the thing inside to the first power. But the chain rule says you have to multiply by the derivative of what's inside. And it's y that's inside here. And the derivative of y is dy dx. Okay. And now to find dy dx, we can just solve this equation for dy dx. Solve for dy dx, because that's what we were looking for to begin with. So let's see, let's move 2x to the other side. So minus 2y dy dx equals minus 2x. But now we can divide both sides by minus 2y. And when we simplify this, we get dy dx equals x over y. But that was our original differential equation. So yes, the equation that we started with, x squared minus y squared equals k, is a solution to the differential equation. So as you can see, depending on exactly how your differential equation shows up or what its order is, solutions to differential equations can take many forms.